Namaskar. After the discussion that what is a function of exponential order and what is piecewise or sectional continuity, we define a function to be of class A. If the function satisfies these two mentioned conditions, then we state that the function is a class A function. On the basis of this statement, we define the article under the heading conditions for the existence of Laplace transform. That means if a function ft is of class A, then L of ft, that means Laplace transform of the function exists. In detail, we can state it like this. If the function ft is sectionally continuous in every finite interval, that means t lies between 0 to n. It can be shown like this. This is our function L of ft, and the value of t we are saying is like this. That means t lies between 0 to n. T is greater than equal to 0 and less than equal to n. Here n is capital. So, if the function ft is sectionally continuous in every finite interval, defined like this, and is of exponential order p, small p, for t greater than n, this is same n here, then its Laplace transform exists. That means L of ft, which is what? F of s, exists. So this is the statement under the condition for all values of s greater than p. So this statement for the condition of existence of Laplace transform can be proved in the following manner. In the proof we will write, you people write down, for any positive number, let us take this number as n. We have, now we will write the equation in this form. This is 0 to infinity exponential of minus of st ft, same function ft into dt. So this is what? Laplace transform of the ft by definition. Now this integration, which is from 0 to infinity, can be written in this form. That is, first we will write 0 to n integration. The inner part will be like this. That means it will remain same as was in this integration, plus n to infinity, and this part will remain the same. This part, this part, this part, these are the same, and we are writing the integration 0 to infinity into this manner. That is from 0 to n, and in the next from n to infinity. And let us write these two integrations which are on the right hand side in this form. That means this part will be equal to I1 plus I2. Let us say it is equal to I1 plus I2. But ft being sectionally continuous in every finite interval, that is from 0 to n. T lies between 0 to n. Write comma and then I1 exists. Correct? Also, ft being of exponential order, p for t greater than n, I2 exists. So, after this, about I2, we are going to write the equation like this. First, see, like this. I2 is this one from in the left hand side, and write like this. This will be equal to 0 to infinity by definition, the same value which we are writing again and again. Then this is less than equal to n to infinity exponential of minus st, ft and dt, and this will be like this. And again we can write this as equal to, less than equal to n to infinity exponential of minus st modulus of ft into dt. We can write this equation into this form very easily. And in the next step, what will we do? We will write this is less than equal to from 0 to infinity, because ft is of exponential order. So this will be written in this form. Minus exponential of minus st m into exponential of pt into dt. Again I must state ft is of exponential order. After writing this, the next step will be this is equal to, less than equal to 0 to infinity exponential of minus sign within the brackets s minus p and t, and here m into dt. So this will be our next step during the solution of this whole part. Now, from the definition of the Laplace transform, we can write that this equation, this quantity rather, this is equal to what? M upon S minus P. This is the simple solution which we solved earlier during the statement of the Laplace transform, after which we solved some simple examples, numericals. From there, I am writing this equation into this form. This equation into this form. So, we can state from here, thus the Laplace transform exists for P, for S greater than P. So, I1 exists, I2 also exists. After discussing this part, we can state that these conditions are only sufficient but not necessary. So, how we can state it? We can prove this statement with the help of an example. And in the form of example, our function ft will be written like this. That is, if we take the value of function, which is naturally ft, equal to t raised to power minus 1 by 2. If we take this example, then we can prove this above said statement, which is that these conditions are only sufficient but not necessary conditions. It is evident after the solution of this example, following example, which is ft is equal to t raised to power minus 1 by 2. Now we will discuss it. This function, again we are discussing above example. This function is not sectionally continuous. So we are stating it that it is not a sectionally continuous function. In every finite interval in the range t greater than equal to 0. For ft tends to infinity as t tends to 0. That means if we will put the value t tends to 0, then our ft will tends to infinity. So from here we can state that the function is not a sectionally continuous function, and we can prove it. It is a very simple proof. Now our next step will be, but t raised to power minus half is of exponential order with m equal to 1 and p equal to 0. In the inequality ft less than m of ept. So all the notations are same. That means we are keeping the same notations to avoid any confusion. So our statement will be like this. ft is less than m of ept. And now we are putting the value of ft, which is equal to t raised to power minus half is less than m into e of pt. So this will be the statement, and it will exist for m equal to 1, p equal to 0. Since t raised to power minus half tends to 0 as t tends to infinity. So it is very simple. Now we have said that function is not sectionally continuous, but it is of exponential order. In this particular example, we are stating like this. But now what happens that the Laplace transform of this function exists, and it can be proved in the following manner. See the equation. In the left hand side, L of t minus half is equal to 0 to infinity exponential of minus st t raised to power minus half into dt for s greater than 0. This equation can be written. Now we are putting t raised to power half equal to x, then half of t raised to power minus half into dt will be equal to dx. So this equation will be written in this form. Laplace transform of t raised to power minus half is equal to 2 of integration 0 to infinity exponential of minus of s into x square and then dx under the condition s is greater than 0. Now we will put some more value in this form. S power half into x is equal to y. हमने ये वैल्यू ऐसे पुट कर दी है यहाँ पर. सोल्व करेंगे, then we will get s power half into dx is equal to dy. So our integration will become Laplace transform of t raised to power minus half equal to this quantity, that means 2s power minus half integration 0 to infinity exponential of minus y square into dy. So this value is achieved. Now there is a formula. which is like this. Exponential of minus y square into dy is equal to under root pi by 2. From this formula, we will put the value in this integration and we will get the value equal to under root pi by s. 2 by 2 will cancel with 2 and remaining will be pi by s square root. Under the condition s is greater than 0. Even if t raised to power minus half tends to infinity as t tends to 0. So we state here, thus the Laplace transform of t raised to power minus half exists even if the function is not sectionally continuous. So this was our condition for the existence of Laplace transform. Thank you.